Example 5.5, stopping the fall of a movie stunt diver, on page 167 reads as follows. The record for highest movie stunt fall without a parachute is 71 meters, which is about 230 feet, held by 80-kilogram A.J. Bakunis. His fall was stopped by a large air cushion into which he sank about 4.0 meters. His top speed was 36 meters per second, or 80 miles an hour, when he reached the top of the air cushion. Estimate the average force that the cushion exerted on his body while stopping him. We're only concerned with when he comes into contact with the cushion to the time that he stops. And because I want to forget his name, I'm just going to call him Bob from now on. So we've got the mass of the guy that I'm now calling Bob is 80 kilograms. Time when he first collides with the cushion, we'll say, is 0. He's got initial position in the y direction of positive 4.0 meters and a velocity initial in the y direction of 36, negative 36, because he's going down, meters per second. I'm going to also note that in my picture that he's got a velocity initial that is downward. Velocity is a vector because its direction does matter. And cushion is going to compress. So the left side is sort of the before, the right side is the after. As far as the after situation, the final time we're not sure of yet. Our y position at final will be 0. You could have had 0 over here and -4 instead of +4 and 0. It really doesn't matter. And velocity final in the y direction is 0. He's going to be stopped. If we want to, or we should, look at this as far as the forces acting on this person. There is a large upward force, which is going to be like a normal force. That's going to keep him from going any farther, and a smaller, which is a single-headed arrow, but a smaller force of his weight downward. So we've got the normal force of the cushion on Bob, and we've got the force of the earth on Bob. Notice the normal force is much bigger, which means we're going to have a net force upward and acceleration upward as well. If we were to represent this with momentum and impulses, we would note that the momentum of Bob initially in the y direction plus the momentum, or I'm sorry, the impulse provided by the cushion on Bob in the y direction. There's also the impulse provided by the earth on Bob in the y direction. All those have to be equal to the final momentum of Bob in the y direction. Momentum Bob final y direction. I'm going to draw a bar chart, a momentum impulse bar chart. And I'm going to draw upward, downward. I'm going to draw a line directly over. The upward part of this bar, it's going to be positive. We're going to have 0, and we're going to have negative. And initially, I guess what we do know is at the very end, Bob's final momentum is going to be 0. He's going to have no velocity in the y direction, so it's got to be 0. He has some sort of an initial momentum taking him downward towards the earth. I'll represent that by a bar that's this big. The impulse that the cushion provides has to be able to cancel out this momentum. It also has to be able to cancel out its weight. So to get to these two negative bars to zero, we're going to have a very large positive bar representing the impulse of that cushion on Bob. Essentially, this plus this has to be equal to this. If I scroll down further to represent that algebraically, it would be oops, I need a pen though. I need a pen, that's very important. Mass of Bob, velocity initial in the y direction, plus we've got our first part of our impulse, normal force of the cushion on Bob in the y direction, plus the other impulse, the force of the earth on Bob in the y direction. And since it is an impulse, it's not only forces, but also the times involved, final minus initial. You have to multiply by that as well, equals our final momentum of mass of Bob, velocity, not initial, final, in the y direction. We can substitute in for the force of Earth on Bob in the y direction. Everything else is essentially going to be the same. Say all this. This is now represented by the positive upward normal force of the cushion on Bob. And this is going to be represented by negative mass of Bob times gravity because it's downward. And we're going to take all that times the difference in times again, and final momentum, mass of Bob, velocity, final in the y direction. I'm going to give myself a little more room. Something we have to keep in mind is that velocity final in the y direction is going to be 0, and we're going to use that to our advantage. And another equation in our book, which is not on the equation sheet for the AP test, unfortunately, is a way to help us out. I believe it's your third equation, kinematics equation, written in a different way to make it easier to work with. We've got our differences in our times equals 2 times our y position final minus our y position initial, all over velocity final in the y direction plus velocity initial in the y direction. And if we know that our velocity final in the y direction is 0, we're going to at least be able to put that there. So essentially our change in time, TF minus TI, or you could put this as delta T, equals 2 times 0 minus 4.0 meters over 0 plus negative 36 meters per second. If we calculate that, our change in time ends up being 0.22 seconds. Another way to take advantage of knowing that final velocity is 0 is with the equation that we were using before. I rewrote it down here, but that's going to be 0. So I'm going to call that term 0. And I'm going to want to try to get that normal force by itself. So I'm going to add MBVIY on both sides. No, I'm not. I'm not going to do that. That would be silly. I'm going to add mass of Bob times gravity on both sides, so that it cancels there, and it's going to be on our right side. Give myself a little more room. So that's going to be equal to mass of Bob times gravity times all this, mb VIY plus NC on B times TF minus TI. I want to get rid of that MB minus VI in the y direction. Minus MB VIY minus MB VIY. That cancels. Now I have NC on B, normal force of the cushion on Bob. Final minus initial times equals mass of Bob times gravity minus mass of Bob, initial velocity in the y direction. Ultimately, I want to get the normal force by itself, so now I'm going to divide by that ratio of times, TF minus TI, over TF minus TI. This cancels, so I'm left with normal force of cushion on Bob is equal to the mass of Bob times gravity minus the mass of Bob, velocity initial in the y direction, over the change in time. And at this point, we can start plugging some numbers in. NC on B equals mass of Bob, 80 kilograms, times 9.8. Now you can have 9.8 can mean acceleration due to gravity, so meters per second squared. It can also mean gravitational field force. Really, it's the same thing. It's just they're written in different ways. I'm going to have it as gravitational field force, newtons over kilograms, minus 80 kilograms times a negative 36 meters per second. All that's got to be over our value that we figured out earlier of 0.22 seconds, so that we end up with a final of the normal force of the cushion on Bob of 14,000 newtons, or 14 kilo newtons, which is a ton of force. He's lucky to have survived it.